So we're going to talk about compact sets. Yeah, tomorrow we have an office hour 3 to 4. For homework too. And of course, I also stay after class. So 1 to 1:30 on Tuesdays. And 12 to 12:30 on Thursdays. All right. So definition. So a subset K of Rn is called compact if for every sequence so you don't have to wait in the lobby. If for every sequence xn and k has a convergent subsequence, there exists a convergent subsequence. That converges to a limit point inside the set. All right, so let's do some examples. So a tough one is showing that so without a theorem showing that 0, 1 is compact is actually quite hard. It's compact. So let's try to show that. So you start with any sequence. Want to find converging subsequence. So converging subsequence. X and K converging to some limit L in 0, 1. Okay, so so first let's recall a theorem. So Bolzano-Weierstrass. What is it saying? It says that any bounded sequence has a convergent subsequence. So the result follows immediately. The result follows because xn is bounded above and below. Okay. All right. Okay, no. So that this says it has a limit. So that tells us that there exists x and k going to L in R. Now we want to show that L is in 0, 1. So by way of contradiction, suppose that L is not in 0, 1. Meaning there exists epsilon naught. For example, so let me actually define it. One good guy is take the inf of L minus S over 2. There exists epsilon naught such that L minus S is bigger than epsilon naught for all S in 0, 1. Is that okay? All right. So now, but if we let epsilon to be epsilon naught over 2, there exists an epsilon such that L minus x and k is less than epsilon for all nk bigger or equal than an epsilon. So if we combine these two, so together, we get, epsilon naught less than L minus x and k less than epsilon naught over 2. So contradiction. All right. Why did we choose that value for epsilon naught? So, because we want this to be true, and we know that this is strictly positive because of this. What else? Yeah, let's do this one. So any discrete set, any finite discrete set is compact. So let's see why. So the proof is very similar. Again, take any sequence AN in S by Bolzano-Weierstrass, we get subsequence, convergent subsequence. A and K going to L in R. Then we want to show that L is in S. And the proof is the same. So we, if you remember, see previous class, see previous notes, where we showed that S is closed. And so L, the limit point S, L is in S. Okay. So hopefully you see a pattern coming up, and we will. So let me see. Shall I do more examples? Yeah, I'll do a few more. Yeah. Okay, so now the set closed 0, open 1 is not compact. Let's see why. So what you have to do is you have to find, so we want to find a sequence xn that has no convergent subsequence. Yeah, so one good choice is take xn to be 1 minus 1 over n. Any subsequence will be of the form x and k, 1 minus 1 of nk, where nk goes to plus infinity. And so x and k goes to 1, which is not in 0, open 1. And so yeah, S is not, so S does not contain subsequential limit points. S is not compact. Yeah, it's a bit tricky. So the set rationals intersect with 0, 1 is also not compact. For the same reason, take any irrational, irrational in 0, 1, like 1 over pi. Then let xn equal x naught. So yeah, I'll just write 1 over pi minus 1 over n. So any subsequence will be of the form 1 over pi minus nk, which goes to 1 over pi, which is not a rational number. Okay. Okay. Yeah, let's do a graph question. So the set e to the x minus x now let me make it like this. For x strictly positive is not compact. In fact, let me make it equal to 0 to further drive the point. Okay. So why is that? Because at 0 you're 1, fine, you even attain it, but clearly you do not attain limit point L equal to 0 is not attained. So let's try to figure out a sequence. Yeah, you can just take xn to just be e to the minus n. Then any subsequence would be e minus nk, which goes to 0, which is not in open 0, 1, which is what this set is. This is that set. Is that okay? On the other hand, the set e minus x, but for x in a compact set, is compact. More generally, we'll prove in the future that if S is of the form f of x and x is in a compact set, and f is what is called continuous, which we'll talk about later, then S is also compact. It's called the Hind-Kanto theorem. So we'll prove this next time. Okay, so let's see, why is this set compact? So start with any subsequence, with any sequence. Xn equal minus En. Then, I mean, we'll do this, we'll prove this general statement again. So step one, Bolzano-Weierstrass gives you subsequence X and K converging to L and R. Two, want to show L is in S, and I'll probably leave this to you. Then again, assume L is not in S, get contradiction. So let's prove the general theorem. Okay. So this is called the Hind-Borrel theorem. And it says that a subset is compact if and only if S is closed and bounded. And the proof would be very similar to what we just did in the examples. Okay. First, let me do the easy direction. So assume closed and bounded. Show compact. So it's very similar. Step one, so take any sequence. Xn, want to show there exist X and K going to L inside the set. Step two, by Bolzano-Weierstrass, since the set is bounded, there exist X and K going to L in the real numbers. Step three, L is in fact inside S because S is closed. Okay. So you don't have to keep proving this. So if you see a set that's closed and bounded, you immediately get compact. We did these 3 steps for the examples over and over again, so you don't have to do this. You can just call the theorem Hind Borrel and you're done in 1 line. Okay, so conversely, now assume you have compact. Let's get closed and bounded. Okay. All right, so yeah. First, let's do closed. What does that mean? If xn in S converges xn to L in R, want to show that L is in fact inside the set. So L contains its limit points. Okay. By definition of compact, there exists X and K going to L tilde within the set. Okay. So now we want to show that in fact L tilde is L, and we will be done, since L tilde is in S. So that will give this is okay. So this is simple. You just do triangle inequality. And that's it. I mean, the first guy is less than epsilon over 2 because xn goes to L. And this guy is less than epsilon over 2 because x and k goes to L tilde. And this is true for all epsilon. So you get L equal to L tilde. Now we show bounded. So we'll do this by contradiction, meaning assume S is unbounded, i.e. You give me any sequence for every sequence of constants going to plus infinity. There exists some element xn in S such that xn is bigger than mn, right? So when we say a set is unbounded, it means you give me any mn and I can give you some set of some element xn of S that is above it or below it, either one. Without loss of generality, take xn to be positive by taking a subsequence. Okay. Now, by compactness, there exists subsequential limit. Which belongs to the set. This is very crucial. So, but this gives a problem. It says that you know, for let's take epsilon equal to 1, then there exists an epsilon such that x and k minus L is less than epsilon. Okay. Right. So if you open this up, you get the following problem. So here you have arbitrarily big things. So this guy goes to plus infinity, but this guy is fixed. So that implies that L is plus infinity, which says that plus infinity is in the set, which is a contradiction. Because plus infinity is not a real number. Okay. Is that true in general? A converging sequence and converging subsequence always have the same limit? Yes. The proof is very similar to what we did for Cauchy. So, yeah. I thought mu n was fixed as well. As we said, mu n is strictly positive. Yeah, mu n is a sequence, right? So, yeah, for every mu n. Like, we can be concrete. You can take mu n to be, you can take mu n to be n. So, yeah, that's it. So that's Hind Borrel. So let's come back to the examples to see how quickly we can get them. The set S is bounded. That's true because indeed we have, you know, for all x and s, we have bounds from top and below, and is closed. Because it contains its boundary. Because boundary of S is A and B, and it's inside S. So by Hind Borrel, S is compact. Right. The naturals one, two, three are closed, is a closed set. See proof for discrete. But it is unbounded. Hence, by Hind Borrel, the naturals are not compact. Is that okay? Right, and the set Q complement 0, 1 is bounded, but it is not closed. Because by homework 1, question 2, there exists irrationals Rn they're just irrationals Rn, and you know, in this interval, for every epsilon positive, and so Rn converges to 1/2, which is a rational number, and so yeah, and 1/2 is not, so 1/2 is not in S, so S does not contain the limit point 1/2. Okay. So by Hind Borrel, Q complement 0, 1 is not compact. Good. So now we'll prove some properties. Of open, closed, and compact. Let's see. So one property is that if U1 to UN are open, then U1 union UN and U1 intersect UN are open as well, are also open. What else? 2. If C1, Cn are closed, then the same is true. Okay. So that means they're closed under finite unions and intersections. So, good. Else. Yeah, and the same is true for compact. We will prove this. Same is true for compact. Okay, and finally, the Kanto intersection theorem. So let's prove this carefully. So it says that if A1 is inside, contains A2 and so on, is a decreasing sequence of non-empty. Compact sets, then the intersection is non-empty. Topology. So everything here is in Rn. The question, Zhongming. Everything is in Rn using a Euclidean metric topology. Zhongming. So let's prove the last one. So if AM is equal to AM plus 1, we get that they have the same intersection. So without loss of generality, assume strict subsets. A1 strictly contains A2, strictly contains A3. So A1, A2, A3, and so on. Okay, that means that there exists xn in an, take away an plus 1 for all n bigger than 1. Right. So but by nestedness, they're all inside A1, and A1 is compact, and so there exists x and k going to L in A1. Claim this L is inside all of them, and so this intersection is not empty. Okay, is that okay? Okay, we're almost done. So let's see. Yeah, so we do it by contradiction. By way of contradiction, suppose that L is not in the intersection. Okay, that means that you can find. Okay, let me draw the picture. So we want to prove L is in the intersection. Suppose no. So L is in, could be in all of them except one. So there exists AM such that L is not in AM. All right. Okay, so now, right. So this is AM and this is L. And there is a positive distance, let epsilon naught be the infimum of L minus S for S in AM over 2. Then for epsilon equal to epsilon naught over 2, there exists n epsilon bigger than m, such that x and k minus L is less than epsilon for all n k bigger than an epsilon and m. Okay. Okay, I'm almost done. So, right, so we get a contradiction, but by nestedness, x and k, so for nk bigger than n epsilon, bigger than m, we get x and k is in a and k, which is inside a and epsilon, which is inside AM. So putting these two together, we get epsilon naught is less than xnk minus L, which is less than epsilon naught over 2. So the usual contradiction. All right, thank you. So I'll stick around for questions. Tomorrow we have an office hour, and that's it. For homework 2, question 1, do you expect us to use MCT to show the convergence? It's up to you. Whatever theorem you want to use, we're not strict about it. Any theorem you would like to use is fine. You don't have to use any particular theorem. Bin Yao? Bin Yao? I mean, okay, you have to be careful because the exponential, you're not allowed to use any properties of the exponential, right? We're building the exponential. So we're defining what the exponential is. So we're not allowed to use any, that's right, yeah, no logarithms. Because we haven't built the exponential. The logarithm, by definition, is the inverse of the exponential. And we have not built the exponential. Is that okay, Bing Yao? Yeah. Well, I mean, you can, Xinyu, I leave it to you. Like, I can't tell you what, but you can use any result you like. Anything from the textbook and from class. Is that okay? Yeah, okay, good. For question you, can I solve part 2 first? Yes, you can. Any order you like. Is that okay, Bin Yao? Okay. Why does xn live in A1? Okay, why does xn lives in A1 imply? No, I knew it's gonna be confusing. I didn't want to say that. I wish I didn't write it like this. This is confusing. So by nestedness, xn is compact. Dot. Because A1 is compact, then we get that. Is that okay, Levon? We already know A1 is compact. Yeah. What else? For question 3, do we have to use the definition of continuous function? Let me see, what is question 3? Don't remember. Oh. Right, so I wonder why I put this question there. Chen, so I will have to move this question to next week because we haven't talked about continuous yet. So it's not, I'm not going to remove it. I'm just going to move it for next week because we haven't talked about continuity. Is that okay, Chen? Chen? Yeah. All right. For question 4, can we assume that summation xn minus xn plus 1, sum of all the difference is the mother sequence? I don't know. What is x and k? I guess it's the subsequence or something. So, yeah, I don't know. I mean, no, like this stuff, if that is true, you have to prove it. This is not obvious at all. Yeah. Is that okay, Sang? Yeah, you will have to prove it. If it's true, I don't know even if it's true. Is that okay? Yeah. Do you want us to use, again, you can use any method you like. There's nothing, we're not very fixed on what approach. Is that okay, Binyao? Any method you like. We're not, we're giving you the hint, which is, but can I use the point W1 defined by Lambert? So, definition, right? So Lambert function is, so Lambert solves, you know, L e to the L equal to 1, right? So that's all we're saying. So you will get something like this. And yeah. So, is that okay, Binyao? Like, we did a question like this before with the square root. So go through the lecture notes. You know, see question with square root 5, I think it was plus an. It's very similar. Is that okay, Binyao? Yeah. With the intersection of Q and 0, 1 not being compact, we took the sequence, but this xn is not rational. Oh, yes, you're right. So the sequence itself, you're right. You're right, Ahmad. I had to take, yes. So I will fix it in the notes, but one way to do this, thank you, is take xn to be, so you have 1 over pi, take it to be, how do you call it? AK 10 to the k, k 0 to n, where AK are the first, are the decimal coefficients of 1 over pi. So I will type this carefully, but that's the idea, because this is rational. Is that okay? Ahmad, is that okay? Yeah, good. A lot of questions. Do we have to solve explicitly for L? No, you cannot even do that. The Lambert function is not explicit. It just satisfies an equation, the one I wrote. Is that okay, Raghuram? So you cannot solve it explicitly. Raghuram, are you there? Is it true that all nested intervals must be closed? All nested intervals must be closed. I don't know quite what you mean. So, yeah, I don't know what you mean, like 0, 1 over n. Yeah, I don't know exactly what you mean. Like you can have open intervals, you know, minus 1 over n plus 1. Does not have a nested interval. Yeah, I don't quite. I mean, the one I wrote, they're nested intervals, right? So. Is that okay? Like, I don't understand. Levon? Is it okay? Levon? I mean, yeah, I don't understand, like, so, I mean, we have both cases. If you take 0, 1 over n, and you intersect them, you get empty set. But if you took minus 1 over n, and you intersect them, you get 0. So you can have both cases. You can have empty and non-empty. Yeah, okay. In today's lecture notes for proving is not compact, why is 0 not in this? Good. So let's say it was. Suppose, that's a good question. Suppose 0 is in S. That means there exists x naught, real number, so that 0 is equal to minus ex naught, right? So you see that this cannot be true. This is only true if x naught is plus infinity, which is not in the reals. So contradiction. Because this is a strictly positive number, right? Oh, I see, yeah. So, yeah, we haven't proved this yet, you're right. It's a little bit tricky. So yeah, we will do this next week. It's called the intermediate value theorem. So we'll do this next week. And it says that, you know, e to the x is continuous. It hits 1 and it goes really close to 0. So it hits everything in between. So 0, 1. Is that okay, Sangu? So we will prove this next week. It's called the intermediate value theorem. Anything else? All right, guys. I'll see you around. Okay, Levon has a question. Yes. What is it? Sure, yeah. Any finite set S is closed. Okay, let's see. So, okay. So, is there any step that was unclear? Something like, was it something weird? Some step that it was like strange? Levon? For AN containing S, this, the first let S. Yeah, okay, so that's right. We didn't actually need it. I was thinking of some other proof, but in the lecture notes that I typed, I didn't include that. We didn't need to do this. So yeah, we never actually used it. I was thinking some other proof, but then I went for something simpler. So in the class notes that I typed online, I didn't include that. I removed it. Yeah, you can just start from the contradiction part. That's right. Thank you. Okay, so wait, Levon, is that okay? Yeah. But what? L is in the sequence AN. No, it's the limit of AN. I don't know quite what you mean. Let me prove it again. So take AN converging to L. AN is in S in the reals. I want to show L is in S. Suppose not. Suppose L is not in S. Then epsilon naught L minus S is strictly positive. And then, right, so then you take epsilon to be this. So there is an epsilon positive. So AN minus L is less than epsilon. But you know, we have epsilon naught is a lower bound for the min of L minus S. So is less than the min of L minus S. So it's less than AN minus L, which is less than epsilon naught over 2. So contradiction. Levon, is that okay? Sure, yeah. Levon, yeah. Yep.
Hi, Thomas, can you hear me?
Yes.
Yes, but for the first part that you said is not necessary. It's just by the definition that AN converges to L, right?
The first part is
like the first part when you let D equals to the minimum of.
So that part D, I didn't have to include it. I was thinking some other proof, and I was like, okay, this is too complicated. So then I moved.
Yeah. Like I'm confused if that part is like true in general.
Oh, like that. Let me see. That
like when you let
this kind of mean of xi minus xj is strictly positive.
Yes, and then you let epsilon be d over 2.
This is true because your set is discrete. Right? So there is a positive distance between them. But as I said, this one, we didn't have to use it.
Yes, but if I use it, like in the end, you concluded that the absolute value of AN minus L is less than epsilon, right?
Right.
And epsilon equals d over 2. But if L, is it possible that L lives in AN?
Then we're done. That would be good. So
but if L lives in AN, then the absolute value of AN minus L is.
Yeah, but remember, right? But remember, we suppose that L is not in S.
Yes.
So L is not equal to xn blah 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 xn, which is L is not equal to A1, A2, so on. So by assumption, if we had this, we're done, right? Because we want to prove L is in S. So yes. Suppose L, yeah, exactly.
No, the part that I'm confused is if L is in reals and if it's in AN, then we have the absolute value of AN minus L is greater than D. And we show that it's less than D over 2. So isn't that a contradiction as well?
Yes.
If L is in AN.
Exactly, yes. So I don't know. Yeah, there's many ways to do this. For some reason, I changed my mind midway. But yeah, both ways work. You're right. Exactly.
But if L is in AN, there shouldn't be a contradiction, right? Because it's possible that
yes, it is, because again, remember, we suppose that L is not in S. So if you somehow show that L is in AN, then you contradict what we assumed.
But if I let L to be in AN, then I have the same contradiction. Like AN minus L is less than D over 2, but it's greater than D as well.
Levon, we're trying to prove that L is in S, right? That's the claim. If you show that L is AN for some n,
yes,
you're done, because AN is in S.
Okay, thank you.
For the last proof today, can you explain what does nested means? Is just remember the proof. Can you explain what does nestedness do? So nestedness comes in. Where does it come? So yeah, so nestedness was used right here. Is that okay, Sangu? Sangu? The one used before. What do you mean before? Where? You can use the audio as well, if you like. Used before where? I don't know. Here? Okay. So which step you want? Yeah, by nestedness, xn is in A1. Is that okay or no? Right, because so you know, xn is in an, take away an plus 1, which is inside an, which is inside A1. Is that okay? Why is it that? No, A1. So here we're not talking about A1 compact is given, right? We already know this is an assumption. Is that okay, Sangu? Sangu, is that okay? All right. Anything else?